Greetings, math fans. All right, so what we're going to talk about today is something called the mean value theorem. It's very scary because it's the mean value theorem. I'm trying to get it renamed to the friendly value theorem, but so far no luck. Anyway, just a couple. This is a little verbiage here. If y equals f of x is continuous at every point of the closed interval a comma b in brackets and differentiable at every point of its interior which is a comma b, then there is at least one point C in AB at which f prime of C is equal to f of B minus f of A all over B minus A. All right, so this is the deal, math fans. This is instantaneous change, and you guys should recognize this one. This is average change. So basically what it's saying is the average, there's a point where the average is equal to instantaneous. So let's take a look what the graph looks like here. Okay, if I give you, here's a function, and we have points A, so this is A comma f of A, and this is B comma f of B. Okay, and here's your secant line. And what I'm saying is, of course, to find the slope of the secant line, it's just going to be f of B minus f of A all over B minus A. Okay, that's just using the yoks, right? y2 minus y1 over x2 minus x1. That's pretty easy. And what I'm saying is there's going to be some point on this graph that is going to be, they're going to be equal. These f prime of C and f of B minus f of A over B minus A is equal. So really what I'm saying is the slopes are equal. So if the slopes are equal, of course, they are going to be parallel. Okay, so that's the whole point of kind of showing this graph. It doesn't necessarily have to be in the middle. I mean, you know, the graph could be a lot of different ways. It could be here, it could be here, but there's some place on that graph that these slopes are going to be equal. Okay, so again, this is the slope of f prime of C. Someplace on that graph, some point C on that graph. Okay, so I'm going to even write in here, if they're parallel, that means those values are equal. And that's why we have equal here. Okay? All right. So let me give you a little more interpretation here. This is a physical interpretation. The instantaneous change at some interior point must equal the average change over the entire interval. So there's in the instantaneous change at some interior point, it's got to equal the average. Okay, so someplace on there. And here, this is actually a real life example, and this will actually kind of clear things up a little bit. If you have a car and the car's average velocity equals 60 miles per hour. So it's equal to 60 miles per hour on the entire trip. Somewhere, the instantaneous velocity had to be 60 miles per hour. Right? Because if you're averaging 60 miles per hour, someplace on there, you had to be traveling 60 miles per hour. That's what I'm looking at here, math fans. So, whatever. I mean, if you went from 0 to 100 miles an hour in a second, sometime, and then I said my instantaneous, I compared instantaneous to average, 0 to 100 really fast. Sometime that instantaneous has to be equal to the average, someplace on the trip. Okay? Because, like I said, if you went from 0 to 100 and you stayed at 100 miles an hour for a long time and your average velocity was like 95 miles per hour, all right, the instantaneous, you had to get to 95. You had to cross that threshold to get to 100 miles an hour someplace. You had to be at 95 at some point to make the average 95. Okay? So that's kind of just a physical interpretation. Well, I want to talk about where these are examples where the mean value, I'm going to call it MVT, where the mean value theorem does not apply. Okay, the first one is here. Okay, and this is going from A to B. And here is, there's your, if you want to look at that, your secant line, if you want to look at it that way. Why does the mean value theorem not apply for this one? Well, it's really obvious because it's not differentiable. And as part of the mean value theorem, it has to be differentiable between A and B. It's not differentiable at that point. Okay, so mean value theorem does not work there. Here's another one for you. Here and there. Okay, why doesn't that work? Well, this one is not continuous. All right, it definitely is not differentiable there as well, but I wanted to show you it's also not continuous because, it's like a piecewise function, right? It's just not a continuous function. So again, if I would connect my A and my B together, that's what it would look like, but the mean value theorem doesn't work. All right, because you can't think of like acceleration. You can't change, velocity, right? You can't go from 5 miles an hour to 50 miles an hour without having to go in between. So that's why it's got to be continuous. Okay. All right. Let's do an example now using the mean value theorem. So show that the function f of x equals 2x cubed plus 4x on the interval -2, 1. Show that it A, satisfies the hypothesis of the mean value theorem, and B, I want you to find value or values of C that satisfy the conclusion. Okay, and so when I say find C, I'm saying at what instant? Okay, so the first part is almost just kind of investigating a little bit. First of all, it's a continuous function, right? There's no issues with not being differentiable. It's a continuous function. So literally, you're just going to say f of x is continuous. It's continuous on the interval -2 to 1. Okay, that's pretty easy right off the bat. And you're also going to say f prime of x, which is equal to 6x squared plus 4. It's also differentiable on parentheses -2, 1. Right? Because there's no issues at all. I don't have to worry about any kind of cusp or vertical tangent or anything. We're good to go. Okay, part B is actually finding that value. So it's really pretty easy. I'm saying, well, where is f prime of C equal to the average, which is f1 minus f of -2 over 1 minus -2. Well, just to figure that out, f of 1, right, you're plugging back into the original problem. It's 6 minus, you plug -2 and you get -24 over 3. So I get 30 over 3, which is 10. That's my average rate of change. And then my derivative is just 6, right? This is the derivative right here. And just plugging that into, just putting C in there. So 6c squared plus 4, and that's going to equal the average. It's really easy. So you get 6c squared equals 6, so c squared equals 1, so c equals plus or minus 1. That's your answer. Pretty easy, right? Okay, let's do another problem here. I want you to show that the function does not satisfy the hypothesis of the mean value theorem on the given interval. Okay, so here's your function. F of x equals absolute value of x plus 1, and your interval is -3, 2. Okay, so really what I need to do here, math fans, I need to rewrite it as a piecewise function, because I need to investigate what's going on with slopes. Okay, it's definitely a continuous function. Absolute value does not, there's no issues at all with being continuous. It's always continuous for an absolute value. Okay, if I write this as a piecewise function, I get f of x equals, of course, you have, our vertex, it's important. Vertex for this problem is going to be 0, 1. Okay, so that means my critical value is x equals 0, right? That's where it changes slope. And so it's going to be x plus 1, where x is between 0, and 2. Okay, the 2 is the endpoint. And then, of course, for negative, you put negative x plus 1. And you get the other endpoint, negative 3 and 0. Okay, with the zeros again being the vertex, so it's where it's changing direction. Okay, so again, we can say the function is continuous but let's look at the derivative. Do you guys agree if I look at the derivative, I get slope is 1, and here the slope is negative 1? So let's write all this other stuff in here. I should just use the inequality, not equal to. Right? That's the case there. So the deal is the slopes are not equal. So it's not differentiable between negative 3 and 2 with parentheses. Now some of you guys were like, Mr. Curves, that's like really easy. Why did we go through all this work? Well, do you guys agree? And let me make a quick sketch of what this graph truly looks like. Okay, so we have the vertex being 0, 1. And this kind of goes up this way. This is a rough sketch, right? Goes this way to negative 3. I guess this goes to 2. It's not an arrow there. Okay, and so here's my going from the average, right? From A to B, if you want to look at it that way. And the reason I need to kind of investigate this is because if I gave you, instead of giving you the domain being between negative 3 and 2, what if I gave you the domain between 1 and 3? Okay, well, let's make it 1 and 2. What if I gave it to you between 1 and 2? Isn't that right here? Isn't that continuous and differentiable? So don't be fooled. Okay, don't go, oh, geez, it's absolute value, so it's automatically not going to be, the mean value theorem is not going to work out. Okay, because if I don't give you the part that's not differentiable, if I don't give you this part right here, and I just give you like one of the sides of that absolute value, it's going to be differentiable and continuous. Okay, and actually, right, the slope of the instantaneous is going to be the slope of the average slope as well, right? All over and everywhere, because you're basically following the line, and the slope is the same no matter where you're at. So make sure you kind of check things out. But in this case here, because I had the corner in that area, right, in the domain, the mean value theorem would not work out. So there is no value of C. So no value of C. Okay? Pretty mellow. All right, anyway, that's it for the mean value theorem. I showed you one that worked out, one that didn't work out. The next topic I want to cover here is another very sad negative topic. It's antiderivatives, which I know we're all pro-derivatives, but somebody's got to be against them, I guess. So antiderivatives. And this is what I mean by an antiderivative. If I give you f prime of x equals 6x squared, you need to actually give me the f graph. So I need to find f of x. So I'm working backwards. Now we're going to do some really basic ones because truly next semester Calc B is all antiderivatives. It's all, we call them integrals. Okay? It's working backwards. And the ones we're doing are going to be pretty easy, just using the power rule and maybe some basic trig, but we're going to get to some problems where it gets actually quite complicated. So I want you guys to think about, what do I take the derivative of to give me 6x squared? Okay, and think about that one for a little bit, and I know we're going to work on this in class, but if you think about it, well, first of all, don't you raise the exponent by 1? So I know it's going to be x cubed, and this needs to move down, right, to multiply to give me a 6. So doesn't it need to be 2? So that is That's my function. But here's one more thing, math fans. If I take the derivative of 2x cubed, I get 6x squared. What if I take the derivative of 2x cubed plus 8? Or plus 10? Or plus 105, right? Aren't all those values acceptable because when I take the derivative, it's 0? So this is the deal. It's f of x equals 2x cubed plus c. C is called a constant. Something we don't know, but that we need to put that in there. Okay, so let's talk about how do you take the antiderivative. We did that one, just kind of looking at it a little bit. So how to take, or find, I should say, right? Antiderivative. If you have f prime of x, and then you're starting out with ax to the n power, this is the deal. You definitely know you raised this by 1. Okay? Then what you have to do is you have to divide it by that power you raised it by. So you increase to whatever it is, but then you have to divide it by that value. Because think about it. If I go from here, then f prime of x, don't I bring that n plus 1 down? So it's a times n plus 1, x to the n power, and then n plus 1. So what happens? They cancel, and you got a x to the n, which is exactly what I start out with. Okay, the only restriction that I have here, math fans, is n can never equal negative 1. That's very important. N can't be equal to negative 1. Okay? So let's try an example here. F prime of x equals 3x to the 5th. Well, it's pretty easy. F of x equals, increase that by 1 and divide it by that new exponent. So you get 1/2 x to the 6th. Is that right? Not quite. F of x equals 1/2 x to the 6th plus c. Don't forget that plus c. That's actually really, really important. Okay, because you have to have that constant there. All right, let's try another example. F prime of x equals cosine of x. So what's f of x? Well, again, what you're doing, you're saying the derivative of what is cosine? Oh, it's sine of x. So right, it's easy. It's really easy to check it, math fans. Just take the derivative of it. What's the derivative of sine of x? Cosine of x. Okay? But don't forget, plus c. Okay, so the last one, just a little more difficult, but if I tell you f prime of x equals 12x cubed minus 6x plus 2. But I also tell you it passes through 1, 5. Well, what that's going to allow us to do is it's going to allow us to find the value of c. So f of x, let's use our rules here, right? Isn't it 12x to the 4th over 4, right? You raise it to that power and you divide it by that, minus 6x squared over 2 plus 2x over 1 plus c. So let's simplify that. We got 3x to the 4th minus 3x squared plus 2x plus c. But now I'm giving you a point. I'm giving you an x and a y, and you have to find c. So it's y is 5, x is 1. Okay, and then just solve it. So 5 is equal to 3 minus 3 plus 2 plus c. So you subtract, this cancels, and we get subtract 2, so we get c is equal to 3. So my answer is f of x equals 3x to the 4th minus 3x squared plus 2x plus 3. Okay, so if you can find c, I'm going to give you more information. If I don't give you any more information, just say find the antiderivative, then make sure you have a c in your final answer. All right, that was pretty easy, but that's it, math fans. Have an outstanding day. Adios. Goodbye.